In June 1948, when Soviet authorities severed all ground access routes to West Berlin, the United States and its Western allies confronted a logistical crisis that would permanently reshape transatlantic airlift doctrine, because sustaining a city of more than 2 million people entirely by air required a level of scheduling precision, aircraft utilization discipline, runway throughput management, and maintenance standardization that had never before been attempted at such scale in peacetime. And the Berlin Airlift, formerly known as Operation Vittles by the United States and Operation Plainfare by the United Kingdom, forced Western planners to convert air transport from a supplementary supply method into a continuous industrial-scale delivery system measured in tons per day, aircraft cycles per hour, and runway occupancy intervals counted in minutes, establishing foundational principles that would later be institutionalized within NATO's collective defense framework. And, during the peak months of the airlift in early 1949, Allied aircraft were landing at Tempelhof, Gatow, and Tegel at intervals of less than 3 minutes, sustaining delivery rates exceeding 8,000 tons of coal, food, and essential supplies per day, a throughput achieved only through tightly controlled air corridors, standardized approach procedures, rapid unloading drills, and immediate departure sequencing that minimized aircraft ground time, often reducing turnaround to less than 30 minutes for smaller transports. And these operational refinements revealed that sustained airlift required far more than aircraft availability. It demanded hardened and expanded airfield infrastructure, disciplined air traffic control capable of stacking inbound flights without collision risk, centralized command oversight to allocate sortie priorities, and forward maintenance staging to ensure that mechanical attrition did not degrade fleet readiness below critical thresholds. And as the blockade continued into 1949, the United States introduced larger capacity aircraft, such as the C-54 Skymaster in place of smaller C-47 transports, thereby increasing per sortie payload and reducing scheduling congestion, illustrating a key doctrinal lesson that fleet composition directly influenced corridor efficiency. And by the time the blockade ended in May 1949, Western planners had accumulated nearly a year of empirical data on aircraft utilization rates, fuel consumption per ton delivered, weather impact on scheduling reliability, and runway stress under continuous heavy traffic, forming the basis for a more analytical understanding of strategic air mobility. And when the North Atlantic Treaty Organization was formally established in April 1949, these lessons were fresh in the minds of military leaders who recognized that future crises might not involve a single isolated city, but the reinforcement of entire theaters under compressed timelines, particularly in the event of Soviet military pressure along the Central European front, and thus the Berlin Airlift became the foundational case study for NATO airlift planning, demonstrating that sustained transnational air operations were feasible if supported by standardized procedures, interoperable aircraft fleets, and integrated command authority, yet also revealing vulnerabilities in runway capacity, weather dependence, and aircraft maintenance endurance that required systematic mitigation. And in the early 1950s, as NATO constructed its integrated military command under Supreme Headquarters Allied Powers Europe, air transport responsibilities initially remained nationally controlled. But alliance planners quickly recognized that effective reinforcement of Western Europe would depend on harmonizing airlift capacity across member states, leading to the establishment of multinational coordination bodies tasked with assessing available aircraft inventories, runway classification numbers across European bases, and cargo handling compatibility, because the Berlin experience had proven that fragmentation in load standards and approach procedures could degrade throughput under surge conditions, And as the Korean War erupted in 1950 and intensified global tension, the United States accelerated production of long-range transports such as the C-1, 2, 4, Globemaster II, capable of carrying heavy vehicles and outsized cargo across intercontinental distances, thereby expanding the potential scope of strategic reinforcement beyond humanitarian sustainment to combat force deployment. Yet this increased lift capacity imposed new infrastructure demands, including longer runway requirements, reinforced pavement to accommodate higher gross landing weight, expanded parking aprons measured in thousands of square meters, and larger fuel storage facilities capable of sustaining continuous operations without resupply interruption. And NATO's early infrastructure investment programs began incorporating these requirements into airfield construction plans across the United Kingdom, France, West Germany, and the Benelux countries, aligning physical infrastructure with emerging doctrinal concepts of layered air mobility, in which intercontinental transports would deliver forces to European reception hubs, and Allied medium transports would redistribute personnel and materiel forward to tactical airfields closer to potential conflict zones, effectively creating a tiered aerial distribution network modeled on the disciplined scheduling principles first proven over Berlin. And throughout the 1950s, NATO exercises tested reinforcement scenarios involving transatlantic air bridges, measuring sortie generation rates per day, aircraft availability percentages under sustained operations, and ground handling capacity at reception bases, revealing that airlift doctrine required synchronization not only between aircraft, but between air transport and rail or road networks responsible for onward movement. Because congestion at reception hubs could nullify gains achieved through high sortie tempo, and therefore NATO planners formalized procedures for reception, staging, onward movement, and integration processes, precursors to the RSOM frameworks that would mature in later decades, embedding the understanding that strategic airlift effectiveness depended on a complete systems architecture rather than aircraft performance alone. And as jet propulsion entered the transport fleet with the introduction of the C-141 Starlifter in the 1960s, NATO airlift doctrine adapted to faster transit times and greater range, enabling more rapid reinforcement curves measured in brigades delivered within 72-hour windows. Yet jet aircraft also required improved navigation aids, longer runways, and more sophisticated maintenance infrastructure, prompting further alliance investment in airfield modernization under the NATO infrastructure program. And as Soviet air defense systems improved in range and lethality, airlift doctrine incorporated dispersal planning, alternate landing site designation, and hardened infrastructure to ensure survivability under missile threat, demonstrating that the Berlin Airlift's scheduling discipline had evolved into a broader strategic mobility doctrine, integrating throughput, survivability, and multinational interoperability into a coherent reinforcement architecture that would continue to expand and mature through successive Cold War phases. As NATO entered the 1960s and the alliance's strategic concept shifted from an early reliance on massive nuclear retaliation toward the more graduated posture, later formalized as flexible response, airlift doctrine underwent a critical transformation from emergency sustainment logic into structured combat reinforcement planning, grounded in measurable deployment curves, because sustaining a city as in Berlin required continuous tonnage flow, whereas reinforcing a theater under conventional threat required synchronized arrival of combat units, command elements, ammunition stocks, and support personnel within narrow operational windows defined by adversary mobilization timelines. And therefore, planners began modeling transatlantic reinforcement not in abstract capacity terms, but in sequential force packages, calculating how many battalions could be flown within the first 24 hours, how many brigades by 72 hours, and how many divisions within the first week. Using sortie rate assumptions based on aircraft availability percentages, average flight duration from continental United States bases to European hubs, refueling intervals, maintenance downtime ratios, and crew rotation limits. And these models were tested against reception-based throughput, measured in aircraft parking slots, fuel hydrant flow rates expressed in gallons per minute, cargo offload capacity in short tons per hour, and onward ground transport availability in rail cars and heavy equipment transporters per day, creating a comprehensive reinforcement matrix that linked airlift tempo to ground absorption capacity. And during this period, the introduction of the C-141 Starlifter significantly altered doctrinal expectations because its jet propulsion allowed higher cruise speeds and greater range than piston-driven predecessors, reducing transatlantic transit time and enabling tighter scheduling intervals between successive departures. Yet, its operational benefits imposed infrastructure demands that not all European airfields initially satisfied, requiring runway extensions to meet pavement classification numbers compatible with heavier landing weights, expansion of taxiways to prevent congestion during peak arrival surges, and installation of instrument landing systems capable of supporting all-weather operations under low visibility conditions. And NATO's security investment program allocated funding for these upgrades, particularly at primary reception bases such as Rhine-Main and Ramstein in West Germany, RAF Mildenhall and RAF Lakenheath in the United Kingdom, and additional facilities in France prior to the reconfiguration of alliance basing arrangements in the late 1960s. And as Warsaw Pact doctrine increasingly emphasized rapid armored thrusts supported by theater-level missile strikes intended to disrupt rear area logistics, NATO airlift planning incorporated dispersal and survivability principles, identifying alternate landing sites across multiple member states, pre-positioning ground support equipment at these locations, and rehearsing rapid redistribution of aircraft in the event primary hubs were degraded, thereby reducing single-point vulnerability within the reinforcement architecture, and the emergence of the REFORGER concept during the late 1960s and early 1970s, further institutionalized airlift as a central pillar of alliance deterrence, because the plan to fly U.S. troops directly to Europe to draw prepositioned equipment depended on precise sequencing between transatlantic sorties and equipment issue procedures, requiring detailed coordination between U.S. Transportation Command elements, U.S. European Command reception staff, and NATO headquarters planners to ensure that arriving personnel could be transported from arrival airfields to equipment storage sites without administrative or transportation delay. And annual REFORGER exercises provided empirical data on personnel processing rates per hour, bus and rail allocation efficiency, and equipment draw time per battalion, allowing planners to refine arrival curves and adjust sortie scheduling to match realistic ground throughput rather than theoretical maximum lift capacity. And throughout the 1970s, advancements in aerial refueling integration expanded the flexibility of transport fleets, enabling direct routing from North America to continental Europe without reliance on intermediate staging in Iceland or the Azores under certain conditions, thereby reducing cumulative delay and increasing responsiveness to crisis activation orders, while improvements in computerized cargo manifest systems reduced paperwork errors that had previously slowed unloading, and alliance coordination bodies worked to standardize pallet dimensions, tie-down procedures, and weight distribution protocols across national fleets, recognizing that interoperability at the pallet level was as critical as aircraft performance in maintaining high-tempo operations. And as these doctrinal refinements accumulated, NATO airlift evolved into a layered, data-driven reinforcement system, calibrated against measurable adversary mobilization speed, integrating aircraft generation, infrastructure resilience, dispersal planning, and reception synchronization into a coherent framework that extended far beyond the improvised yet disciplined corridors of 1948, embedding air transport as an operationally decisive variable in Cold War defense planning. By the mid to late 1970s, NATO airlift doctrine had reached a level of institutional maturity in which reinforcement was modeled as a continuous operational flow rather than a series of isolated deployments, because alliance planners increasingly treated the transatlantic air bridge as a managed throughput system comparable to a supply pipeline, defined by quantifiable constraints at every node, including aircraft generation rates, tanker support availability, air corridor deconfliction capacity, runway acceptance intervals, ramp space measured in aircraft parking positions, and cargo handling productivity expressed in tons per hour. And this system's perspective was reinforced by intelligence assessments that emphasized the Warsaw Pact's capacity for rapid concentration along the Central Front, compelling NATO to reduce decision latency between political authorization and aircraft launch, and to rehearse surge operations under compressed timelines. And during successive REFORGER iterations, the United States tested the ability to deploy tens of thousands of personnel within days, measuring cumulative arrival curves against projected adversary timelines, while European reception bases were required to demonstrate continuous 24-hour operations with minimal aircraft ground time, often targeting turnaround windows of 90 minutes or less for personnel transports under high-tempo conditions. And heavy-lift aircraft, such as the C-5 Galaxy, introduced additional complexity because their outsized cargo capacity allowed air movement of equipment previously restricted to sea lift. Yet their runway load requirements demanded that only certain primary bases with reinforced pavement and extended runway length be designated as hubs, leading to the formalization of a hub and spoke reinforcement architecture in which wide body transports delivered cargo to major reception airfields and smaller tactical transports redistributed supplies forward to dispersed operating bases, and survivability considerations became increasingly prominent as Soviet theater missile doctrine evolved, prompting NATO to integrate hardened aircraft shelters for high-value assets, pre-identify alternate landing sites across multiple member states, and establish rapid runway repair capabilities to restore operational status in the event of missile damage, thereby ensuring that reinforcement flow could be sustained even under degraded infrastructure conditions. And coordination with civilian aviation authorities was codified into crisis airspace management plans that temporarily restricted commercial traffic in designated corridors to preserve military arrival sequencing, reflecting a recognition that reinforcement scale could exceed peacetime air traffic patterns and required prearranged priority protocols and advancements in navigation technology, including inertial navigation improvements and enhanced instrument landing systems. Reduced weather-related uncertainty, enabling tighter scheduling intervals and improving reliability of arrival forecasts, while maintenance planning incorporated predictive modeling of aircraft availability to prevent cumulative degradation of fleet readiness during sustained surge, drawing directly from Berlin era lessons regarding preventive maintenance cycles, yet applying them now to jet-powered transports operating intercontinental missions. And NATO's Air Transport Committee and related planning bodies increasingly relied on computerized data analysis to simulate reinforcement under varying threat scenarios, adjusting sortie generation assumptions to account for tanker diversion, weather disruption over the North Atlantic, or temporary loss of a primary hub, thereby stress testing the airlift doctrine against realistic friction rather than ideal conditions. And by the close of the decade, the alliance possessed a reinforcement architecture in which airlift capacity was quantified, infrastructure hardened, procedures standardized, and multinational interoperability institutionalized, transforming the experience of emergency supply in 1948 into a sophisticated, survivable, and continuously exercised strategic mobility doctrine central to NATO's conventional deterrent posture during the height of Cold War tension. As NATO moved into the 1980s, airlift doctrine became even more tightly integrated with alliance war planning because the strategic balance on the Central Front increasingly depended on whether reinforcements from North America could arrive quickly enough to offset Warsaw Pact numerical advantages during the opening phase of a conflict, and therefore airlift was no longer evaluated solely as a transportation function, but as a time-sensitive operational variable embedded within detailed campaign models that compared projected pact force concentration curves with NATO reinforcement arrival timelines, expressed in personnel per day, battalions per 72 hours, and cumulative combat power available by specific decision points. And this analytical integration required planners to refine every component of the airbridge architecture, from aircraft generation at continental United States bases to reception efficiency at European hubs, and at the generation end sortie modeling incorporated aircraft availability rates calculated as a percentage of fleet readiness after maintenance cycles, crew duty limitations measured in flight hours, tanker refueling support capacity expressed in available refueling brackets per day, and routing adjustments to mitigate weather disruption across the North Atlantic, while at the reception end runway throughput was measured in maximum heavy aircraft landings per hour under instrument flight conditions. Ramp occupancy was quantified in parking positions per wide body transport, and fuel hydrant systems were evaluated in gallons per minute to ensure that refueling would not become the pacing factor limiting turnaround, and to reduce aircraft ground time. NATO expanded prepositioned ground handling equipment, including K-loaders and cargo transfer vehicles compatible with standardized 463L pallet systems, ensuring that unloading operations could proceed continuously, even if individual equipment units failed. And survivability considerations were refined further, as Soviet theater missile capabilities, such as the SS-20, raised concerns about concentrated basing vulnerability, prompting dispersal planning that distributed arrival aircraft across multiple pre-designated airfields within Western Europe, each equipped with compatible navigation aids, runway load classification numbers sufficient for heavy transports, and pre-positioned support teams trained in rapid reception procedures. And these dispersal drills were incorporated into major exercises, including Able Archer and subsequent REFORGER cycles, which tested not only arrival speed, but adaptability under simulated infrastructure degradation, measuring how quickly reinforcement flow could be rerouted without collapsing cumulative arrival curves, and the evolution of secure communications and early computerized tracking systems enabled near real-time visibility of aircraft position, cargo manifests, and personnel status across transatlantic routes, allowing NATO headquarters to maintain a unified reinforcement picture and adjust sequencing dynamically when disruptions occurred, thereby reducing the lag between detection of friction and corrective action. And as aerial refueling doctrine matured with expanded tanker fleets, planners gained flexibility to extend routing options or bypass compromised staging bases without sacrificing mission range, reinforcing the resilience of the air bridge. And by the mid-1980s, NATO airlift doctrine represented a fully institutionalized strategic system characterized by layered mobility, hardened and dispersed infrastructure, standardized interoperability down to pallet dimensions and load plans, integrated RSOM processing, predictive maintenance modeling, and continuous multinational exercise validation, demonstrating how the disciplined scheduling principles pioneered during the Berlin Airlift had been expanded into a technologically advanced, survivable reinforcement architecture capable of delivering large-scale combat power across an ocean under the most demanding conditions envisioned during the final decade of the Cold War. By the latter half of the 1980s, NATO airlift doctrine had become inseparable from the alliance's broader conventional deterrence posture, because reinforcement timelines were explicitly embedded within operational plans governing the defense of the central region. And these plans assumed that transatlantic airlift would deliver combat-ready personnel in carefully sequenced waves aligned with prepositioned equipment draw and onward movement schedules, creating a time-phased deployment data structure in which arrival curves were plotted against projected Warsaw Pact offensive tempo. And to support this, synchronization alliance planners refined reception staging onward movement and integration procedures, to the point that personnel processing capacity was measured in troops per hour at designated reception airfields. Bus and rail allocation rates were calculated against peak arrival windows, and equipment issue sites were evaluated for simultaneous battalion throughput without creating administrative congestion, and such precision required sustained exercise validation, leading to increasingly complex REFORGER iterations in which thousands of U.S. personnel were airlifted to Europe within compressed 72-hour periods, testing not only sortie generation, but airfield resilience under simulated missile threat, nighttime dispersal, and degraded communications conditions. And these drills reinforced the importance of hardened infrastructure, including runway repair kits capable of restoring damaged pavement within hours, redundant fuel storage calibrated in millions of gallons to sustain continuous operations without immediate resupply, and pre-positioned ground support equipment sufficient to handle multiple wide-body transports concurrently, and coordination mechanisms between military and civilian aviation authorities were further refined to ensure rapid transition of airspace control during crisis, temporarily prioritizing military corridors while rerouting commercial traffic, reflecting the reality that reinforcement scale could exceed normal peacetime air traffic density, and advances in computerized tracking systems enabled centralized monitoring of aircraft availability, cargo load factors, and personnel status across the Atlantic, allowing NATO headquarters to maintain predictive arrival estimates and adjust force flow in response to maintenance delays or weather deviations, while tanker integration provided routing flexibility that mitigated reliance on fixed staging bases, enhancing survivability against potential interdiction. And as political change began to unfold in Eastern Europe, after 1989, the alliance initiated a comprehensive review of force posture. Yet airlift doctrine remained a retained capability rather than a redundant relic, because the infrastructure investments, interoperability standards, and layered mobility principles developed since Berlin had created a durable reinforcement architecture, adaptable to emerging contingencies beyond the traditional central front. And thus, by the time the Cold War formally concluded in 1991, NATO possessed a mature, quantitatively modeled airlift doctrine grounded in 4 decades of iterative refinement, exercise validation, and infrastructure modernization, transforming the emergency improvisation of 1948 into a structured multinational system capable of delivering sustained, synchronized combat reinforcement across intercontinental distances under demanding operational conditions. As the Cold War entered its final phase between 1989 and 1991, NATO's senior military planners conducted comprehensive strategic reviews that reassessed force posture, basing distribution and reinforcement requirements in light of political transformation across Eastern Europe. Yet even as the Warsaw Pact began to dissolve, the alliance did not abandon the airlift architecture it had painstakingly developed since 1948. Because by this point, air mobility doctrine had evolved beyond a single adversary model and had become a foundational instrument of alliance flexibility, rooted in standardized infrastructure, interoperable procedures, and quantifiable throughput capacity. And the enduring value of that architecture was evident in the way reinforcement modeling had been institutionalized, with arrival curves, sortie generation rates, runway acceptance intervals, and RSOM processing capacity integrated into NATO planning software and staff procedures rather than retained as isolated national calculations. And throughout the late 1980s, planners had continued refining predictive models that incorporated aircraft maintenance availability percentages, tanker support allocation, weather probability matrices over the North Atlantic, and alternate landing site dispersal logic to ensure that even under degraded conditions, the air bridge could sustain measurable daily reinforcement targets, often expressed as battalion equivalents per 72-hour window, and infrastructure investments made under the NATO Security Investment Program, including strengthened pavement classification numbers for heavy transport acceptance, expanded fuel hydrant distribution networks, and standardized cargo handling equipment across member states, ensured that reception bases retained capacity well above peacetime commercial usage, preserving surge margin for unforeseen contingencies, and multinational coordination mechanisms, from the Air Transport Committee to integrated airspace control planning, had created habitual interoperability that reduced friction between national fleets, allowing aircraft from different member states to operate interchangeably across designated reception airfields without procedural mismatch. And as political dialogue replaced confrontation, the alliance recalibrated reinforcement force levels downward, yet retained the structural principles derived from Berlin and matured through REFORGER and Able Archer cycles, embedding airlift as a standing capability rather than a crisis improvisation. And when the Cold War formally concluded in 1991, the doctrinal journey from the 3-minute landing intervals over Tempelhof to the highly modeled, data-driven transatlantic reinforcement architecture of the 1980s stood as a testament to sustained institutional learning, demonstrating that NATO had transformed emergency air supply into a resilient, multinational, strategic mobility doctrine measured in quantifiable capacity, survivability, resilience, and synchronized integration, capable of projecting power across oceans within tightly defined operational timelines. And although the geopolitical landscape had shifted, the airlift doctrine forged across 4 decades remained embedded within alliance planning culture as an enduring expression of collective defense grounded not in symbolic gesture, but in calibrated, validated performance. When viewed in its entirety from 1948 through 1991, NATO's airlift doctrine represents one of the most sustained and methodical transformations in alliance military planning, because it began as an improvised response to blockade and evolved into a fully institutionalized reinforcement architecture embedded within operational models, infrastructure investment programs, and multinational interoperability standards. And the Berlin Airlift provided the initial empirical proof that disciplined scheduling, centralized traffic control, rapid turnaround procedures, and maintenance rigor could sustain thousands of tons per day under continuous pressure. Yet it also exposed the fragility of ad hoc coordination without permanent structures, and over the subsequent 4 decades, NATO converted those lessons into enduring doctrine by standardizing cargo pallet systems, aligning runway load classification numbers across member states, expanding reception hubs capable of handling wide-body jet transports, integrating aerial refueling to extend routing flexibility, and developing RSOM processes that synchronize personnel arrival with equipment draw and onward movement, thereby transforming airlift from emergency sustainment into a time-phased deployment mechanism quantified in sortie generation rates, aircraft availability percentages, runway throughput intervals, and battalion-equivalent arrival curves. And as Warsaw-Pact mobilization doctrine emphasized speed and mass, NATO responded by embedding reinforcement modeling within campaign plans, rehearsing surge operations through REFORGER exercises, dispersing reception bases to mitigate missile vulnerability, and investing in hardened infrastructure to preserve flow under degraded conditions, and the maturation of computerized tracking and communication systems in the 1980s further strengthened integration by providing near real-time visibility into aircraft movement and cargo status, enabling dynamic adjustment to friction rather than static reliance on ideal scheduling. And by the time the Cold War concluded, the alliance possessed a strategic air bridge architecture that extended far beyond the corridors over Berlin, encompassing layered mobility from intercontinental lift to tactical redistribution, survivability planning under missile threat, multinational interoperability down to pallet dimensions and load plans, and validated surge capacity capable of delivering large-scale combat power across the Atlantic within compressed operational windows. And thus NATO's airlift doctrine stands as a cumulative product of iterative refinement, technological modernization, and institutional coordination, embedding the lesson that strategic mobility is not defined by aircraft alone, but by an integrated system of infrastructure, scheduling discipline, standardized procedures, and continuous rehearsal, ensuring that collective defense commitments were supported by measurable, executable reinforcement capacity rather than declaratory assurance alone.